So you guys have a good break? Yeah. I will begin with a word of prayer. Heavenly Father, we thank you for this afternoon and for these students. Just pray that you be with us today. Help us to just learn more math together. Help the students to ask good questions as they have them. And just pray that they would be encouraged as they work on this course to do their best each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. 7713 is the exciting top hat code. So I hope you guys noticed that there is a assignment which is due, I believe, Wednesday, and for you guys. And the assignment is pretty simple. You just need to watch the two videos I posted last Wednesday, right? And fill out the answers. You don't actually have to work it out, right? But there's like 10 long divisions I've done. I ask you to write the answers to the questions that I posed there. And I used long division in those videos to solve the problems, right? So to get the most out of it, of course, you should actually work through those long divisions for yourself, you know? But I don't require you to do that and write it out or anything like that. I'm just saying, for your own sake, it would be good if you practice them for yourself, right? The fact that I can produce them and show them to you is not the same as you doing it, right? There's nothing to replace you sitting and doing it by yourself in an undistracted, you know, peaceful context where you can focus on the math, right? Okay, so that said, that's due Wednesday. Make sure you do it. It's worth 10 points of the participation, so that's a fair amount, yeah? And
hey, buddy, come on. We all see you, come on.
That is the loudest anything anyone has ever done so quietly in my class. I mean, like... So I know why people don't use this stuff. It smells like popcorn or something. It's just weird. All right. So today I need to talk to you guys about reverse problems. To start with, that's what we're going to do. Reverse problems. So what do I mean by that?
Doing a problem in reverse.
Doing a problem in reverse. That's right. Well, here's the basic template. Is we're given data and asked, since Star Trek The Next Generation, it has forever become data. So it's given data and asked to create f of x which fits the data. Or find data if we must. I thought we were past that. See here. All right, so I'm going to start us out with an example. All right. So example 1. Suppose we've got graph. So our question is to find polynomial of least degree which produces such a graph. All right, so what's the graph I'm talking about? Here we go. We're going to bounce, we're going to cross, and we're going to bounce, and we're going to cross again. All right, and I'm going to tell you the bounce happens at, let's say, -4. This happens at -1. This happens at 3. And this one over here happens at 5. All right? And I'm going to also tell us that the y-intercept is given to be, I don't know. Let me think about this for a second. $144. Obviously not to scale, right? Okay. So this y-intercept is at 144. All right, so how do we find a graph of such a thing? So I'm just going to do the first one, then I will let you guys contribute more to the thinking as we go on here. But this one, we're just get us started here. F of x. So we're going to put an A to allow the the vertical scale of it. All right, I look at it. I've got an x minus 4. I've got a minus 4 x-intercept here. That means I want an x plus 4, right? However, because it's bouncing, I want an x plus 4 squared. Then I get to minus 1. That means I want an x plus 1. I don't need to square it because this time it doesn't bounce, it just crosses, right? Then I get over to 3. So that means I want an x minus 3. But x minus 3 alone would make it cross, so I need to square it to make it bounce. All right. And then I get over to 5. So I have an x minus 5. That will work. Now, we need to pin down what this value is for A, though. All right? So how do I figure that out? What does 144 mean on that graph? Right, so notice that 100, it's the y-intercept, yeah, which means 144 is equal to f of 0. Right? When we plug in 0, we get out 144. So that's going to be equal to A, 4 squared, right? So we've got a 4 squared times 1 times minus 3 squared, right? Times minus 5. Plugging in 0 into the formula. But if you look at this, what you've got there is A times 12 squared times minus 5, right? In other words, you've got 144 equal to, what is 144? 144 is 12 squared, right? So this reduces to 1 is equal to minus 5A. So A is apparently equal to minus 1 over 5. So the answer for this problem is f of x equals to minus 1/5 x plus 4 quantity squared x plus 1 times x plus 1 times x minus 3 quantity squared times x minus 5. There you have it. That's your answer. That has a graph which resembles the given graph and is of least degree that you can do it. Question. Does the general shape of the graph make sense with the value that we found for A? Does that look right? I mean, think about it. So this is an even power. It should be an even power graph, right? And it's opening down, so we should have a negative leading coefficient. That's what we found, a negative leading coefficient, right? And what's the degree? 2 plus 1 is 3, plus 2 is 5, plus 1 is 6. Sixth degree, even, leading coefficient negative, from a million miles away, looks like a bowl that opens down. That's our graph. So that checks. Is good? Yeah? Let's do another. Same instructions, same as example 1. All right, let's give us a graph here to chew on. How about this? Whee! All right. Should always draw my axis second if I was smarter. There we go. I made the mistake of last class of making one of my x-intercepts 0.3. Watch the video, see how that turned out. Stupid, stupid, stupid. Okay, whole numbers are our friends for examples. So let's say that this is at minus 2, this is at minus 1, this is 0, this is 1, this is 2, all right? And I need to give you some other data point, all right? The other data point I'm going to give you is that f of 3. Well, I'm going to say that this point over here is like 3 comma, I don't know, 40. All right, let's find the polynomial of least degree that has a graph that looks kind of like this. Right? So let's build it. So I start us out, f of x. I'll put a constant out front just to allow for rescaling, yeah? And then you guys get me started. What's my first thing? X plus 2. Then what? X plus 1. Very good. And then just, what about the 0? Yeah, just put x, right? If you want, you can put x minus 0 to make it look the same, but it's just x, right? And then I heard an x minus 1, then x minus 2. Now, why no squares? There's no bounds here, right? So no squares. Then what? I need to figure out what that a is, right? How do I do that? What does 340 being on the graph mean? F of 3 equals to 40. What's that? Is that what that point tells us, right? Every point that you have in a graph tells you a value of the function for the graph you're looking at. Okay? So we just have to put that into practice. We've got 40 is equal to f of 3, which is, if we plug 3 into this formula, a times 3 plus 2 is 5, 3 plus 1 is 4, that's just 3. 3 minus 1 is 2, and 3 minus 2 is 1. So 5 times 4 times 3 times 2 times 1 is 120. That's 5 factorial. It's in my other class I'm teaching right now, that number. But anyway, it's 120. And so what do we got? 40 equals to 120a. A equals to 40 over 120, also known as a third. Yeah. So therefore, f of x equal to 1/3 times x plus 2 times x plus 1 times x minus 1 times x minus 2. And there is your answer. Do you guys see how the game is played? Yeah, so this is just the problems we were doing before in reverse, right? So if you ever find yourself in the place of needing to like write a college algebra test, this is how you can make up problems, you know? Now, question, why don't you think about something? Could you multiply these out?
Yeah.
You could. Did I do it?
No.
Why didn't I do it? Because, yeah?
You said you wanted it in the least degree.
No, that's not it. But it's a good comment. It's just because I didn't say otherwise. I mean, I didn't put any constraints on the formula, right? I didn't say put the formula in standard form. Standard form is when you multiply it out and do, you know, x to the n plus dot, yeah, expanded form, right? The so-called standard form. So if I don't ask you to do that, don't do it, right? Every time I teach this class, there is a subset of students in this material that they have this like ingrained like need in the time pressure of the test to multiply these out. It wasn't asked, probably, almost certainly was not asked, because that's not interesting to this course. Multiplying these out is really not that interesting. It is something you should be able to do, but, you know, the point here of these problems is to understand the factor theorem and the interplay between the x-intercepts and the zeros and the factors in the polynomial. Like multiplying it out is not interesting. So I'm telling you this now in the interest of hopefully convincing some of you to not do this on the next quiz and test, right? Let this not be a self-fulfilling prophecy I'm making right now, right? After I grade quiz 2, let me not come back to you and go, hey, come on, right? So, all right. I have said my piece. I tried to stop you. Did you pan? Okay, cool. Example 3 is going to be a little bit different. Now, there are examples where you have to multiply out, but it'll be more obvious which one that is, okay? Our example 4 will be like that. Example 3, find a polynomial of least degree whose graph is non-negative for x less than or less than 0 and has x-intercepts of, let's say, -2, 0, 1, 0, 3, 0, and contains point. Now, just a second. I gotta think about this in my head for a sec. Four or 5. This is the first section of college algebra I've attempted an example this difficult. I did an easier example in the previous 2 sections, but you guys are awake, so we can do it. We're going to try anyway. So I start out pretty much the same, right? I'm going to want f of x. I need, some a to adjust, right? If I have an x-intercept of x, I need an x plus 2, right? I have a x minus 1 from that, right? X minus 3. Now now we have to think a little bit. I want the graph to do what? I want it to be non-negative for x less than 0. What must happen at -2 for that to be a possibility? Yeah, it's gotta. So I'm saying if this is going to be non-negative for x less than 0, right? Think about it. If our graph looked like this, if this was -2, right? And the graph crossed through there, like going this way or going that way, you'd be in trouble because it would be positive here, negative here, positive there. I mean, it's going to flip side. You can't do that. We must have a bounce here in order to keep it non-negative. So we have to put a square here, logically speaking.
Okay, so does it want the negative add?
Right. So it could be 0. It could be 0 at -2, but that's it, right? And I think we're going to be able to do it with that. All right, let's see if it works out. So what else do we know?
So do all the points are all non-negative?
Well, this would have a graph that looks something like what? It bounces at -2, right? And then it crosses at 1. And then it crosses at 3. And then supposedly we're going to put the point 4, 5 on it. So I think that we can make do with that data. I think it's not, I mean, you can make up data that's impossible to fit if you're not careful, all right? There's a lot of flexibility with polynomial models, but you can bend it so much that it breaks. It's possible. Like if you give me 4 points and ask for a parabola that goes through those 4 points, there's no guarantee I can find such a parabola. Right? You give me 3 points, say find a line that goes through 3 points. Can you do it? Is there a line through 3 given points? Maybe, maybe not, right? Depends on whether those points are collinear. It is an interesting question to ask which line is closest to 3 given points, right? That's the problem of, that's the linear regression, right? Or the best fit line that you guys do in like physics lab or whatever, or chemistry. Yeah? You ever do the best fit line? You guys know what I'm talking about? The error bars and all that fun stuff. Woohoo. Okay, so I think this is a rough sketch of what that looks like. I think it's logical to try this. Yep.
Why can it go below the graph on the right side and on the left?
By assumption, I'm saying whose graph is non-negative. So it was in the problem statement. I said look for a function, at least whose graph is non-negative for x less than 0. That was imposed on us by the problem.
Yeah, but why can't it go like cos 3, 1?
Because I didn't say anything about x positive. I didn't put any restriction. I didn't say always positive. Now, if I said that it was always non-negative, that would be also an interesting problem. That would just make us bounce everywhere, right? That's actually a good way to make this problem less confusing, is to say, you want a graph that's non-negative, right? If you say the graph is non-negative, that would force you to put a bounce on each x-intercept. That'd be a good modification for this example. Excellent question. So now we can figure A out, right? Because we got the 4, 5 point, so we got to plug that in. What does 4, 5 mean? That means f of 4 equals to 5, right? So this means f of 4 equals to 5. And so let's do that. F of 4 equals to 5, but that's equal to A times, 5 plus 2 is 7. Got to square that. 5 minus 1 is 4. 5 minus 3 is 2. So you got yourself a 56 times 7, which is, I don't know, 350 plus. Did I do wrong? Oh, I plugged in 5? Oh, man. Well, that's no good. Thank you. This is why we can't have nice things. Let's see here. Plug in 4. 4 plus 2 is 6. So I've got a 6 squared. 4 minus 1 is 3. 4 minus 3. Well, that's nicer. Well, thank you. That made my problem easier to do the math here. What? 36 times 3. Yeah, 108. So we've got A is equal to 5 over 108. Okay, so there you have it. Our answer is f of x equals to 5 over 108 times x plus 2 quantity squared times x minus 1 times x minus 3. That is a function that fits the data, and you can't get away with anything smaller degree working, right? So that's it. What if I had instead of giving you the point 45, think about this. What if instead of 4, 5, I had given you, I don't know, 4 minus 5? Well, how would that put a wrinkle in our plans? Yep.
The x-intercept of the y-intercept would have been down. So when it bounced, it would have been negative.
Yeah, it would have been, so like 4 minus 5 would have been here, right? If we, you're dead to me. I've only hit one student this semester so far. So, not in the head.
I know how to come 340.
Let's see here, so I guess, I wanted a green. Oh man. So if I had instead put this point down here, if I had given you 4 comma minus 5,
You have to square the x minus 3, right?
that's right, we would have had to make it bounce off 3 in order to get it to reach down there, right? You would have had to make the graph instead look something like this, right? And so if that was the problem, that would have forced you to put an x minus 3 squared there and work through it. I think this to me looks like a good bonus problem on the next test or something. This is pretty hard what I'm talking about.
It's too hard, man.
That's why it's bonus, yeah.
If that were the case with the 4 negative 5, how would we know that it would bounce off of 1 and then flow through the
Ooh, yeah, that's right. Well, you're right. So he's right. To get to 4 minus 5, You could also have some kind of pattern like this, bounce off the -2, bounce off the 1, and then cross through the 3. You could have done that.
Is either one wrong or that both right?
Unless I give more data, that is an ambiguous problem. There would be 2 answers. Yeah, cool. Which is why if I'm smart, I won't assign that problem because grading it would be a nightmare. But anyway. Okay, enough of this. Example 4. Nonsense. Given parabola y equals f of x has vertex -2, 7 and 3, 10 on its graph. Find formula for f of x in standard form. Now this one here is different, right? Because, well, it's about a parabola, right? So a parabola, we know all kinds of stuff about parabolas, right? Like a good quarter page of your formula sheet should be occupied probably with formulas for parabolas, right? I mean, you got quadratic formula, you got your, formula for the vertex, you got the different forms of the parabola, like x-intercept or standard form. Or, in this case, I think we want vertex form, right? What's the vertex form for the parabola? You guys remember? I'll remind you. So f of x is equal to a times x minus h quantity squared plus k. This puts the vertex at h comma k, right? So here, hk is equal to what? -2, 7, right? That's given. So in this case, h is equal to -2 and k is equal to 7. So I plug that in, and I've got a times x plus 2 quantity squared plus 7. So, okay, great. Now, how do I figure out what a is? What else do I know? The point, yes, the point 310, right? This means that f of 3 is equal to 10, right? So I have 10 is equal to f of 3, which means I plug 3 into this formula. I get a times 3 plus 2, which is 5, squared plus 7. Solve for a. So we get 3 is equal to 25a. Apparently a is equal to 3 over 25. And that tells me then that my f of x is equal to 3/25 times x plus 2 quantity squared plus 7. Now, if I had not written the words in standard form, we'd be done, because that's a formula, right? That would be an answer, a perfectly fine answer, if I had not written the words, the annoying words, in standard form. Because I've written the annoying words in standard form, it obligates us to put the formula into standard form. How do you do that? Yep.
Wouldn't it be 10?
10?
Not 3?
What have I done? Not 10.
You subtracted 7.
What did I do?
Oh. You subtract 7.
Like where you know for a equals 25a, he's asking wouldn't it be 10 or 25?
Did you subtract the 7?
What happened to the 7?
You subtracted the 7 in the red. Yeah.
You subtracted the 7.
Would you add something?
You're supposed to add 7 to the 3.
But he moved it to the other side, so it's
F.
Subtracted 7 from 10 to give you the 3.
Okay.
Oh, from here to here?
Yeah.
Yeah, I subtracted 7 from both sides. And okay. Sorry. I'm debating which part of it you guys are. So we're simpatico. Are we good? All right. Great. No. You guys are so mean. Let's see here. I know it's your brand, but you could, take a break. 3/25. X plus 2 squared is x squared plus 4x plus 4. And then I got plus 7, right? So what that gives me is 3/25 x squared plus 4 times 3, which is 12, over 25. All right. And then I got to figure out what's 4 times 3. What is 12 over 25 plus 7? That's what? 12 plus 175 over 25, right? How many cents is 7 quarters? 7 times 25? Well, 8 times 25 is 200. It's like, 8 quarters is $2. So like 1 quarter less, $1.75. I don't know. I think about money. But 7 is 175 over 25. I've got to make a common denominator to add the fractions. So long story short, 12 plus 175 is 187. 187. 187 over 25. There you go. Standard form. Woohoo! Can I explain which? Ooh, nice marker.
How do you go from, how did we, can you explain what you did?
What I did to
Yeah,
get.
so how did you get like the x squared plus 4x squared?
This is x plus 2 quantity squared. So when we FOIL out x plus 2, we get x squared plus 2x plus 2x plus 4, which is x squared plus 4x plus 4. So just multiplying out the x plus 2. And then I distribute the 3/25. It's like 3/25 times x squared is just 3/25 x squared. 3/25 times 4 is 12/25. And then the last one's more complicated because 3/25 times 4 is 12/25, but I got to add 7. And so that, when I convert that to 25ths, I get 175.
So it's the 7 times 25 is the 175?
Yes.
Okay.
Yeah. What was the question? Yeah.
So, my whole thing is when you get that middle part right there, x squared plus 4x. Where'd you get that from?
That's the x plus 2 squared. So this multiplies out to that.
Do you want to get rid of the fractions, though? I mean,
I don't think I can.
can you not?
I don't think these reduce.
Can you
Yeah.
not multiply everything by 25?
I cannot because this is the function. It's not an equation, so we can't just multiply it. Yeah. So this is another kind of problem. There's a few of these, I think, sort of things in your homework. Yeah. All right, so that said, I'm going to move on here. So work on your homework about these things. Come back, ask me questions about them after you have. All right? And now we are moving on to graphing rational functions. Woohoo!
I gotta take a picture of this. Don't worry with that.
Don't worry, I'm not erasing that anytime soon. What is a rational function?
We gotta do more for like number 4, man. That's a hard one. You want something else?
So what is a rational function? A rational function has the form f of x equals to p of x over q of x, where p of x and q of x are polynomials. Is a rational function. So we want to talk about how to graph rational functions. All right. Now I'm going to give you a, an algorithm, let's say, for doing it, much like I gave you an algorithm for how to graph polynomials, right? But I'm not going to do that yet because it's going to take me too long to state the algorithm at the moment. I think it's better use of our time to just kind of do some examples. So when I state the algorithm, hopefully at the start of next class, it'll make more sense to you what the algorithm is saying, okay? So here we go. Example 1. Oh, thank you. Muchas gracias. Graph y equals to, let's call it f of x. We got x squared minus 1 over, let's say, x minus 3 squared. All right, like that, yeah. We're going to graph this. Yeah. So the first order of business is to factor anything that we can. And so here this is x plus 1, x minus 1 over x minus 3 squared. All right?
Do you factor the lower part?
It's already factored. The denominator is already factored. All right, so, okay, great. Now, I'll make the number line over here so you guys can follow it easier. So here's my f of x. I've got critical numbers at, let's see here, like minus 1, at 1, and maybe over here at 3. All right? And so I make a sign chart. What happens if you plug in like 4? 5, 3, 1 squared. So it's positive, right? So we start out positive here. And then this is a square. So we stay positive. In some sense, we bounce. I say in some sense. And then at 1, well, that's just x minus 1, right? It's an odd power, just power 1, so we flip signs. And then, again, x plus 1 is an odd, it's just power 1, right? So we flip signs again. Okay? If you want, we could figure out, let's just double check our work. What's f of 0? What we got? Minus 1 over what? Minus 3 squared, right? So minus 1/9. It's negative between minus 1 and 1. That's good. Okay. All right, so now we can kind of make a graph. All right. All right, so let's see here. There is an x-intercept. There's an x-intercept at minus 1. And there's an x-intercept at 1. Right? But at 3, something different happens. At 3, we have division by 0, right? So at 3, there's a vertical asymptote for the graph. So I'll draw a dotted line there at 3. Okay? 3. And this one's a little bit trickier than some ones we run into, because this one here is an example of an improper rational function. So in the sense that the degree of the numerator is equal to the degree of the denominator, all right? That means we can rewrite this as a polynomial plus a proper rational function. A proper rational function is one where the degree of the denominator is larger than the degree of the numerator. So the way to do that is with long division. So just for you guys, we're gonna divide x squared minus 1 by that, which is x squared minus 6x plus 9. Right? X minus 3 squared is x squared minus 6x plus 9. I repeat, x minus 3 squared is x squared minus 6x plus 9. A third time, x minus 3 squared is x squared minus 6x plus 9.
What is it again? I'm kidding.
I want to see. But I predict in 4 minutes someone's going to ask me what this step was. Let's see here. So anyway, my point is we can divide here, put a 1, and then we've got x squared minus 6x plus 9. There's your fourth time. We subtract those guys, and we get 6x minus 10, apparently. All right, so what that means is that y is equal to 1 plus 6x minus 10 over x squared minus 6x plus 9. So this right here is what I said we call a proper rational function. Proper rational function. You notice that the degree of the numerator is 1, the degree of the denominator is 2. A proper rational function has the very nice property that as x goes to plus or minus infinity, the denominator wins, which means that it's like 1 over a really big number on either side of extremes. So this piece goes to 0. This piece goes to 0 as x goes to plus or minus infinity. And so what happens to the graph then is whatever happens here is that's the large scale behavior of the graph. In other words, this thing looks like y equals to 1 if you're really, really far away from the origin, which is to say that there's a horizontal asymptote of 1 for this graph. Y equals 1 is a horizontal asymptote for this graph. You can cross horizontal asymptotes. The point is that eventually you're drawn into it, all right? And I probably need to extend this past here to make this graph worth anything. All right, so let's do it. I figured out that the y-intercept was minus 1/9, so that's kind of here-ish if I'm doing scale. Okay, so what happens? We're positive, right? We cross to negative. So it's something like this. Cross to negative. Let me make this minus 1/9. Okay. And then we cross at 1 again, right? And then what happens? This is a vertical asymptote. That means the function blows up there. And so here, it's like a volcano. If you stay pluses on both sides or minuses on both sides, pluses from both sides at a vertical asymptote is like a volcano up. If you have minuses on both sides, it's like a well or hole, or whatever, or upside down volcano. There you go. And then like this, and then what happens is it asymptotically goes to 1. That's what we mean by horizontal. A horizontal asymptote just tells me where the graph is headed eventually. And so there you go. That's y equals f of x.
So it breaks
It breaks.
along the vertical asymptote?
It breaks at the vertical asymptote, right? You could think about this as bouncing off. My brother likes to think about this as bouncing off infinity. Anytime there's an even factor, it's a bounce. It's either a bounce off the x-axis or it's a bounce off infinity. Anytime it's an odd number, it's a cross. It either crosses the x-axis or it crosses through infinity. Next example, I'll show you crossing through infinity, quote unquote. All right, next up, we will graph example 6. Let's look at y is equal to x minus 2 over x times x squared minus 4. All right. So what we got going on here is x minus 2 over x times x plus 2 times x minus 2. So there's a fair amount going on here. The new thing about this example relative to the last example is, look at this. We got x minus 2 here and here, right? So anytime this happens, you get what's called a hole in the graph. Hole in graph. And so if we look at that, this reduces to 1 over x times x plus 2 for x not equal to 2. So this is called the reduced function. So one way you could graph this is to graph the reduced function and then just add a hole where there's a hole in the graph. All right, so let me go through the usual song and dance here. Make our number line. What are our critical numbers? We've got minus 2. Yeah, minus 2, 0, and 2, right? And what happens with that formula? Let's look at the original, because the reason for that is we've got to be careful. It could end up being that we cross 0 at the hole, and then if it actually crossed, we could get confused by the, so it's best to use the original one. That's a good question. Okay, so we will come back to use the reduced function in just a second, though. All right, so we put in like 3, plus, 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 right? So we start out pluses. At 2, we're looking for factors of x minus 2. How many x minus 2 factors do we got? We got 2. That means we don't change signs. So we stay positive because there's 2 x minus 2 factors. X, there's just one of them, so we flip signs. X plus 2, we flip signs again. All right, now we can graph. What's the y? So this one is proper rational function, which means that eventually the graph is drawn into the x-axis. All right, there's no interesting horizontal asymptote like in example 5. And where are my vertical asymptotes at? I got one at 0. And I've got one at minus 2. Right? And let's see here. So this graph looks something like this. Whee! And let's see here. Oh, it stays negative, right? So it's got to turn around. Right? It never gets to the x-axis between minus 2 and 0. So it has to bend back like that. Then it bends up here, like so. And then it's got a, well, where is that? Where, let's see here. So then it does like this. Now at 2, there's a hole in the graph. Where is that? How do you figure out the y-coordinate of the hole in the graph? Plug in 2 into which, if we plug 2 into the original formula, we're out of luck. Because that would give a division by 0. Into the reduced is the way to do it. That's where the reduced function comes into play. So we do 1 over 2 times 2 plus 2. So that hole is actually at 2 comma 1/8. That's where the hole in the graph is. So this is how we graph rational functions. It's a lot like how you solve the rational inequalities, right? You identify all the critical numbers, you put them on the number line. Just the new thing is we need to figure out how to graph around vertical asymptotes and how to also mind x-intercepts at the same. This had no x-intercepts, did it? Right? So some do, some don't. But this one, you notice that we don't bounce off infinity. My brother says that this is like crossing through infinity. It's like you're going off to infinity and then coming back over here. I don't know, whatever. If it makes sense to you, great. If not, the point is that we have the only way we can cross the x-axis in terms of the graph is either to go through an x-intercept or to have one of these vertical asymptotes where we flip from plus to minus or vice versa. Yep.
That parabola looking thing right there, does it matter where the vertex is, or is that just?
To know where the vertex is to take calculus. You taking calculus?
That's enough for me.
I am.
You don't want to take calculus?
Oh, no, I would love to.
You'd love to. I feel like I feel like I'm being sold something with this answer. I don't know. It feels, you got it?